All right, guys. Hey, I'm going to be doing lesson 5.1 notes today. We're going to talk about different ways to identify linear functions. So the first definition that you need is what is a linear function? And what I want you to write for that is that this is a function whose graph forms a straight line. A function whose graph forms a straight line. And then you guys are used to identifying whether something is a function or not. We just did that in chapter 4. So the way that you tell if something's a function or not is by looking at, do those x's repeat? But we're not just being asked today if something's a function. The big idea is that you guys are going to be looking at whether something is specifically a linear function. So there are lots of different kinds of functions. Some functions are linear functions. Some of them are quadratic. Some of them are exponential. Those kinds of functions we'll be doing later on. But in chapter 5, it specifically is focusing on linear functions. So whether those graphs form a straight line or not. Standard form for a linear equation looks like this. Ax plus by and then equals capital C, like that. And this is the very first form that you'll learn. And so the big idea is that by looking at that equation, you can tell whether something is linear or not. So again, we're focusing on this word linear, not just if something's a function. Okay, so we can tell whether something is linear by looking at the 4 different things below that are shown in the table by looking at a graph, a table, ordered pairs, and then also an equation. So I'm going to zoom in on the graph part of this first. And if you're looking at a graph, all that has to happen is that the graph has to make a straight line. So I want you to write makes a straight line. And so if I draw a picture of what that would look like, we've got an x and a y axis. We've talked about like discrete graphs and continuous graphs. And all sorts of types of graphs. We've seen U-shapes and V-shapes and lines. But specifically, if something's a linear function, it has to make a straight line. So it could look like that. Or it could even be like a horizontal straight line like that. It could even be a vertical line. So if I were to draw a vertical line, it could look like this as well. Or it could, even look like that. Okay, all of those things are straight lines, and so all of these are linear functions. You can also tell whether something is a linear function, by its table. And the way that you tell by a table is that there will be a constant change in the x's that correspond to a constant change in y's. Which is kind of wordy, so I'm going to draw an example of this as well, just like I did for the graph. So if you're looking at a table, you would look at the x and the y columns in the table. X is always our first, y's are always second, and you would look at the change. So the change would be like, okay, whatever numbers are here, what is it going up by each time, or what is it going down by each time? And you would do the same thing with the y's. You would say, okay, what are the y's going up or down by each time? And then we would look at the slope of those and see whether it was constant or not. Remember that the word constant means that it's going to stay the same. So those slopes or those changes would stay the same every single time. If that happens in a table, it's linear. Okay, so we're not looking at just whether the x's repeat or not. That's whether something's a function. We're looking at, okay, is this a linear function? And so then you have to look at the change in the x's and the change in the y's. The next thing that we look at is ordered pairs. And for ordered pairs, that's just points. So I'm going to write points up here. But what I do with points is I just make a table. And then I check for the exact same thing that I do over here. Okay. So again, I would make that table of points that they gave me using an X column and a Y column. And I would look at, once I put the points in the table, I would look at, okay, how much are the X's going up by or down by each time? And I would look at, what about the Y's as well? And you'll see actual examples with numbers in just a minute with those. Okay. The last way we can tell if something is linear or not is by looking at its equation. And there's a couple things that have to happen in an equation. Okay. So the first thing is that the X and the Y both have exponents of 1. Okay, you will not see any other exponents. There's not going to be a 2 exponent or a 3 exponent anywhere in the problem. And remember that when we don't see any exponents on X or Y, that means that the exponent is 1. Okay, that's why up here in standard form, if you look at the X and the Y up here, they don't have any exponent, because if they don't have any exponent, then we automatically assume that that tiny little exponent is a 1. We just don't write it in there because it's not very proper. So I'm going to erase those little ones. Okay. If I come back down here, there's a couple other things that have to happen in an equation. Your X and your Y can't be multiplied together. Okay, X and Y cannot be multiplied together. So they can't be smushed by each other. And then one more thing that has to happen is that X and Y can't be in the bottom of a fraction or up in an exponent or under a radical sign, like that. Okay? So they can't be in the bottom of a fraction, they can't be up in an exponent, and they can't be under a square root sign, because then it would not make a straight line graph when we actually plugged numbers into it. Okay, so if you need to pause the video at that point to copy all of that down, feel free. But I'm going to go on to the next part of the practice problems on the next page. Normally, if I was here, I would give you guys a bunch of different things to cut out for the next part of this. But because I'm not there to cut it all out and do all of that, I'm just going to give you a bunch of examples of things that are linear functions and then a bunch of examples of things that are not linear functions. Okay, so I want you to again highlight or circle that word linear. Okay, linear, because we're not just looking at whether something's a function or not. Okay, that was in chapter 4. We're really focusing on whether it's a linear function. Okay, so I'm going to give you some graphing examples. Okay, if you have a picture of a graph and it were to look like this, that would absolutely be linear. It would be linear because the graph forms a straight line. That's all that matters there. That's all you need to look at. Here's another graph example as well. If I gave you a graph that was like a horizontal line like this, it's still forming a straight line, and as long as it forms a straight line, it is linear. Okay. Here's an example of a table that would be linear. X's and Y's, and I'm going to put some numbers in the table. In the X column, I'm going to put 2, 5, 8, and 11. And then in the y's, I'm going to do 4, 3, 2, and 1. Now, I'm not looking at whether the x's repeat or not. That would be if I asked you whether this table was a function. But to tell whether it's a linear function, I have to look at what the x's are going up or down by. From 2 to 5, it's going up 3, so plus 3. And then from 5 to 8, it's going up 3 again. And then from 8 to 11, it's going up 3 again. And then I look at the y column as well. The y column, from 4 to 3, it's going down 1. 3 to 2, it's going down 1 again. And 2 to 1, it's going down 1 again. So I'm not looking for whether those numbers in purple match to the numbers in green. I'm looking at the slope of them. And so what I would do then is I would do the change in the y's and divide that by the change in the x's. So what I'm going to do now is take each of these numbers and form a fraction with them. So if I look at the first one would be negative 1/3. If I look at the next row, I have negative 1 and 3 again. So I would write negative 1/3 again. And for the last set, it was down 1 and up 3 again. So I would write negative 1/3 again. Because these are all the same, that means they have the same slope, and if it has the same slope, then it's linear. It's not always that obvious though. So here's another table of x's and y's. And let's see, I'm going to do 0 and then 5, and then I'm going to do 15, and then I'm going to do, let's see, 30. And then for my y's, I'm going to do, let's see, so if I was to put that in my x and my y column, and I was to look at the change in x's again, from 0 to 5, it's going up by 5. 5 to 15, it's going up by 10. And from 15 to 30, it's going up by 15. If I look at my y's, from 0 to 15, it's going up 15. 15 to 45 would be going up by 30. And then 45 to 90 would be going up by 45. And it kind of looks like it's not going to work out. But when you set up the slopes and you look at the change in the y's over the change in the x's, and I set up those as a fraction, I would get 15 over 5. For my next fraction, I would do 30 over the 10. And for my last one, I would get 45 over 15. And if you actually do 15 divided by 5, that's 3. So is 30 divided by 10, that's 3 as well. And 45 divided by 15, that's equal to 3 as well. So even though it's kind of hidden, these all have the same slope as well, the slope of 3. If your slope is constant, if it equals the same thing, then it's linear. So you can see in kind of an obvious table, like the one up above that I did first, and then you can see kind of a not obvious example as well. The other way that you can tell is by looking at equations. And so there's lots of different equations that are linear. Some of the more obvious ones would look like this: y equals 2x plus 5, right? If I wrote that down, it looks like y equals mx plus b, so a lot of you will recognize that as linear anyway. But if you go back up to our notes from earlier and the equation, and you look at those requirements, the x and y's both have exponents of 1. And you can see in our equation, they both have exponents of 1. The x and the y are not being multiplied together, so that's good. And the x and the y's are not in the bottom of a fraction, or up in an exponent, or under a square root. So that would be an example of a linear function. Some less obvious ones would look like this: y equals 7. All right, even though there's only a y in this problem, they still only both have exponents of 1. The x and the y are not being multiplied together, and they're not in the bottom of a fraction or up in an exponent or under a square root. That would actually be a horizontal line, okay? And horizontal lines are straight lines. So if I gave you something like x equals -5, that x and y, it only has an exponent of 1. They're not being multiplied together. They're not in the bottom of a fraction, up in an exponent, or under a square root. So that one would actually make a vertical line, but it's still linear. It still makes a straight line. It's just vertical, and the other one, y equals 7, was horizontal. So some less obvious examples. Another equation that I could give you would be like y equals 1/2 x minus 8, right? The x and the y follow all of those rules that we mentioned on that first page of notes. All right, so let's look at some things that are not linear functions then. So down here in the area where it's not linear, I'm going to draw a couple different graphs for you. And the deal is that with the graphs, the only thing is they can't make a straight line. Okay, so I can draw anything I want to as long as it's not a straight line. Here's one. That's not a straight line, so it's not linear. I could draw something like this. Okay, that's also not a straight line, so that is not a linear function automatically. If I was looking at a table, okay, and let's see, I'm going to do x's and y's on my table. We'll go 0, 1, 2, 3. But then I'll do 5, 7, 8, and 10. If I look at what my x's are jumping up by on the left here, 0 to 1, it's going up by 1. 1 to 2 is going up by 1. And 2 to 3 is going up by 1 as well. But if I look at the y's, it's going up by 2. 7 to 8 is just going up by 1. 8 to 10 is going back up by 2. Some of you will be able to look right at that and be like, oh, yep, that doesn't work because they're not constant. But when I actually make my fraction here, my first fraction would be the change in 2 over 1. My next one is going up 1 and over 1. So let's see, we would write 1 over 1. And then the last one, I was going up 2 and over 1. So I would write 2 over 1. If I actually do this division, 2 over 1 is 2. 1 over 1 is 1, and 2 divided by 1 is 2. So these are not the same slope. If they don't have the same slope, it's not linear. And then lastly, I can give you lots of equations that are not linear functions as well. For example, if I did like this, 2 up to the x power, that is definitely not linear, because you are not allowed to, if you go back to that first page of notes, you're not allowed to have x's or y's up in the exponent. Here's another example. If I did the square root of x plus 3, you are not allowed to have x under a square root or y under a square root. So that breaks the rule. It's not a linear function. Even if you had something like this, y equals 3 over x, like that, not okay, because we can't have x's or y's sitting in the bottom of a fraction. If you see something like this, y equals x squared minus 5, we know that when we see a squared in a problem, that the squared is going to make a u-shape. Doesn't make a straight line, so it's not a linear function. If you see absolute value bars, something like this, absolute value bars, we know that those make a v-shaped graph, so that's not a straight line, which means it's not a linear function. What else? We could even do something like this. 3 equals xy plus 5. Right? X and y are being multiplied together right here, and that's not okay. So I'm going to kind of highlight all of the issues. On the first equation, the x was up in the exponent. That's not okay. The next one, the fact that the x was underneath of that square root was not okay. X sitting in the bottom of a fraction here was not okay. The squared on this one was not okay. Absolute value bars, we know those make a V shape, so they are not a linear function. And then in the last example, x and y were being smushed by each other, which means multiply, and that can't happen for something to be linear. So if I zoom out, guys, you have lots of examples of things that are linear functions, and also lots of examples of things that are not linear functions. And that'll do it for lesson 5.1 today. So you guys can get rolling on your homework with the rest of class time.